All right, everybody ready? Our next presentation is shore-based teleoperation of deep submergence ocean exploration vehicles on UNOLS vessels by Stefano Suman, if I pronounced that right, plus 3 others. I think we'll come give that right now. Just stand here and eat the microphone.
Thank you, everyone. I'm Stefano Suman. I'm a research engineer at the WIS Deep Submergence Lab, where I've been for the last 11 years developed software and technologies for vehicles of the lab and the NDSF vehicles. In this presentation, we just wanted to make people aware of certain directions in which we're going with the vehicles that could improve the operation of such vehicles, and especially displacing operators as needed from the ship to shore by taking advantage of internet connectivity and VPN links.
Point it out. Oh,
sorry, I'm a bit middle.
Okay. The vision comes from the realization that compared to the past in which the internet connectivity was the exception, nowadays the internet connectivity is more or less the rule, although with its own challenges in terms of uptimes at times. And the status quo is that the ocean exploration is affected by staffing, especially
I'm sorry, technical difficulty. Okay.
Ocean exploration is affected by pandemics, like we're just being one, we still all have masks, and there could be others in the future. So the possibility of continuing ocean exploration with people operating the vehicles from shore is an attractive possibility. The shrinking size of the ships, for example, the regional class research vessel, puts more of a premium on berthing. So operating these vehicles with a full staff of 10 people on the ship may not be viable anymore in the future, and the need to displace those people is more important than ever. And staffing in general, finding people who go to sea for extended periods of time is always hard. And sometimes there could be a medical condition that contribute to the difficulty of staffing. The television solution, the teleoperation solution, so the displacement of staffing from ship to shore could improve this aspect. So by leveraging always connected UNOLS vessels as access point using their satellite infrastructure, and especially the upcoming low Earth orbit satellites that are supposed to provide a step change in bandwidth and latency that could enable newer method of teleoperation, economies of scale, and existing exploration vehicles prototyping platforms. We want to go to a final goal of fleets of connected assets that can be operated from shore. So to explore the opportunities provided by newer technologies and the increase of connectivity of the ships, we focused on 4 areas so far, which one of those is the real-time engineering troubleshooting with AR. I think everyone in this room at some point in their career had, the endless email thread about troubleshooting something at sea from shore. With a higher bandwidth and lower latency, we're starting exploring holographic technology so that the technicians in the field can provide can view in their field of view holograms provided by the shore operators. In this case, we attacked them on the Nautilus last year, where a technician on the ship, which has a HoloLens, which is a holographic device, which we can see the technician in the lower left corner, and which could see in her own field of view the pinout in this particular case of a device which was malfunctioning, and the malfunction was detected from shore. The pinout was put as a hologram in their field of view by electrical engineering in Florida, and the software engineer in Woods Hole was operating, turning on and off devices, the device itself from shore using VPN. So this translated what could have been a day or two troubleshooting operation in a 10 minutes operation with a technician on the ship, having less expertise than would be required otherwise to deal with this. Another field in which we focused on is remote checkouts. Operation of the vehicle for research vessels includes a lot of checkouts that before dives or before deployments that still has to be done by person. So is your acoustic modem talking? Is it operating at the right frequency? Are the safety releases still working right? Do we have to use a multimeter for that? So all these operations are being automated and put into edge processing devices, which detect the proper functioning of the devices under test and warn the remote operator onshore of the proper functioning. Essentially, in terms of teleoperation is similar in some ways to telepresence, in which they share the same tools to some extent, the internet connectivity and VPNs. So telepresence tends to take the scientist and move it to shore. The teleoperation concept attempts to take the operator on the shore and bring it to the ship. Another part which is more and more relevant as data becomes a ubiquitous item that is necessary for the vehicles to process in real time and provide as a tool for the scientists to explore the ocean is having data people that could be onshore and logging remotely into the remote system, the VPN, to process data at the edge. And this is something we have tried still on the Nautilus tech demo. In this case, where on the left side we can see the near and the right vehicle was transmitting data in real time via an optical modem to shore, which an optical modem is a high bandwidth, low latency wireless underwater communication tool. And the people on shore from their home office were able to log in remotely into the system and process them up, which you can see in the bottom left of the screen. So this again improves scalability of improving staffing and time to deliver data products to the scientists on the ship. Remote operations is the concept about once all the other aspects are satisfied that I explained before, is piloting, watch standing, and do all the operations that otherwise require a person on the ship. In this case, we have in the center picture, we have our Zach from Hui in his own office during the cruise of last year, being able to pilot the vehicle with a joystick over satellite in the VPN link and withstanding its mission, which is something that typically is done during longer missions. On the left, we see the same technology applied to a World 30 Days cruise that was in January of last year, in which we were able to do some mission planning and withstanding of the Sentry vehicle, which was operating in the Pacific Ocean from the rooms in at Hui, and including getting data back to the scientists on as needed to the scientists on shore, and also some remote manipulation. So some groups, which Camille's lab in our group, developed some VR system to get around the latency, the problems caused by latency that we introduced in the remote manipulation for RV applications. We're also starting to see how we can use, how can I integrate using VPNs and satellites, development AT operations using DevOps practices, which are state-of-the-art in developmental technologies. This all sounds great. These are still all tech demos though. In the lower left, we still see what is a a common seen nowadays for ROV operation on a ship. So a pilot, a data person in the corner trying to process data, and other scientists in the background. So how do we go from reality to dream? The dream is like being able to operate fully a vehicle, an underwater vehicle from shore using potentially VR technology in the future. Well, what are the next steps in this? The next steps will be, given that these vehicles would utilize UNOLS connectivity, try to establish a working group to build routine teleoperation capability and some sort of expectations in terms of uptime and connectivity, bandwidth, uptime, latency latency vehicles, deep submersion vehicles that could operate out of UNOLS vessels as with remote persons routinely, and deal with the cybersecurity implications and with distributed teams communication protocols and methods and safety and fail-safes. We will discuss more this topic and especially the generations of working groups or service agreements tomorrow in a breakout session at 2 p.m. for whoever is interested. Any question?
Hopefully you'll join the breakout session and ask lots of questions there. She's checking Huba for questions. Alice.
Yeah, is some of this being done already by institutions like Schmidt, or are you going beyond and OER? Are they doing a lot of this already, or are you going beyond what they're doing?
I think Alice wanted to know whether Schmidt, whether you were going beyond what Schmidt or what was the other one?
OER.
Whether you're going beyond what Schmidt and OER have been doing.
I mean, I know they've been doing a lot of.
Yeah, this is an opportunity for us to for the community touch base, and in the breakout session tomorrow, if Schmidt, I know that there's some Schmidt people attending. If you would like to attend that session, see where we're at in terms of technologies and where we can collaborate to make this a more routine operation across multiple vehicles.
And I mean, are you looking to like 90% of your staff from like adjacent crews, or?
Let me repeat that. She's asking, are you looking to eliminate 90% of your staff from Jason Cruises?
I don't think that's possible with the size of JSON, but I think it's possible to cut it in half, probably.
Okay, yeah.
Right, the rest of the questions go to the breakout session. Sorry. And I would like to introduce our speaker, Dr. Deborah Kelley, who is a professor of oceanography in the School of Oceanography. Explorer has been 50 submersible dives to depths of as great as 4,000 meters and have routinely used robotic vehicles to reach ocean depths. Her current research examines the linkages between submarine volcanoes, underwater hot springs, and how they support sunlight. In 2000, she was part of the team that discovered the Lost City hydrothermal field, hosting 150,000-year-old limestone chimneys that rise 180 feet above the surrounding seafloor. This remarkable ecosystem is like no other in the world's oceans, hosting microbes that thrive in methane and hydrogen-rich 90-degree sea fluids with properties of liquid graynel. She has participated in over 40 blue water cruises, leading many of them. Since 2014, Dr. Kelley has been the director of the National Science Foundation's Regional Cable Array, the largest underwater scientific observatory. This array includes about 900 kilometers of underwater high power and bandwidth fiber optic submarine cables, which connect 150 instruments offshore from Oregon directly to the global internet. She's passionate about providing students opportunities to directly participate in seagoing research. This has taken about 160 students to see on global class research ships. And with that introduction, maybe we have the complete technology transfer.
Almost.
Okay, so share.
Oh, you gotta hit the share button.
I did.
And then, yeah, there you
Oh,
go. And
There we go.
share sound.
Do I have to get out of share now? Stop share?
Yeah, stop share.
It's good that I'm leading a technology program. Mm,
This one?
Yep, and then that
This
guy.
one, and then that guy.
There,
Okay.
cool. Really? Yeah, we're fine.
Okay.
Stop it. Okay.
So it
Great.
looks like we can see you on your own camera.
Super.
And that's all excellent. Off you go.
Can I get rid of this guy?
We want you to use the mic.
Yep.
So.
I want this guy to go away. I don't think people need to see it.
There you go.
I want to get rid of him. Anybody know how to get rid of him? Oh, well. Okay. Go ahead. This guy?
There we go.
Perfect. Thank you. Cool.
Okay.
Thank you so much.
Eat the mic.
All right. Well, welcome. It's a really great pleasure to be here. I see numerous friends in the audience. And I just want to say thank you. First of all, I've sailed, as you'll see, in a lot of the big boats. I started out as a undergrad music major, Russian major, ended up working full-time for John Delaney and fell in love in 1980. Took me for the first time to go to sea on the old Thompson. And then in 1980, I did a lot of dredging. 1982, we found the first hydrothermal system. To this day, it's one of the most active ones around with 150-foot tall chimneys. And then highlight was in 2014, we finished the installation. It was an 83-day cruise on the Thompson for the cable array. So I'll give you a little overview of the cable array. It's a little different than probably what you've seen before. And then I want to dive into one of the great places we get to go is axial seamount, which is the most volcanically active submarine volcano off our coast. But I just want to say thanks to everybody on the boat because they are like family to me. And some people I've known since actually close to 1980. So it's a testament to how great the team is on the boats. In the early days, we would, if we were lucky, we'd go out with Alvin maybe once a year, get some dives and Endeavor. We went there pretty much every year. And you guys all know, like when you're at sea, things change really rapidly. And so this is an example of a hydrothermal chimney that we used to see each year, and it fell over. And so this one, this one we cut off, and it grew 6 feet in a couple days. And we're always out there in storms, and a lot of the major processes in the oceans that impact our planet are storm driven. And then also I want to show you something you may not know about is when volcanoes erupt, they stream billions of microbes from the seafloor. So unless you're there, John started thinking about, all these things where if you're not there in the right time at the right place, you're going to miss these events. And so that was about maybe 20 years ago when the internet was really exploding and communication cables. And so he dedicated his life to get a program, the Ocean Observatories Initiative funded. And we're part of that, but we're the only component that has a fiber optic cable. And NSF funded it. It's supposed to be funded to operate for 30 years. And there was, I think I'll say it later, but there was about almost 300 scientists involved in the planning, putting in proposals of where we should focus our instrumentation. And it spans everything from coastal environments, clear off to blue water environments at axial seamount. So as part of that, and part of the proposals that drove this, there were 16 of them. It spans many of the processes that operate in our oceans, everything from tsunamis, seismic events. The waters off our coast are some of the most biologically productive in the world. We focus on methane seeps, a lot of energy resources, microbes, and a big focus on climate change. So this is, we had a great partnership with L3 Meripro, and I'll show you the primary nodes that provide the main power and bandwidth. But this is a 900-kilometer cable of submarine fiber optic cable. These are big substations on the seafloor, and I'll show you that. They provide the power and communications from Pacific City, Oregon, offshore to axial seamount, and then it turns south and runs up to 80 meters water depth. And then within the key environments of working, we have smaller substations, and I'll show you pictures of those in a minute. But what this does is it provides two-way communication in real time at the speed of light, up to 1,000 hertz. There was an experiment that just did, so big data. We have state-of-the-art cabled moorings that provide water column information 24/7. And again, these are all two-way communication, so we can respond to events. And we have over 150 cabled instruments now from the seafloor through the water column. And one of the drivers for this, initially recognizing that technology changes rapidly, is that it's highly expandable. We don't use anywhere near the power or the bandwidth yet, and also use it for education. So a broad community and hopefully policy someday. Just to give you a sense of scale, so if you flipped it around and looked from Seattle, it would cross 3 states. And at the time, the way they lay these, I'll show you a picture of the ship, the way they lay these cables, it's almost a 500-foot boat, steam's 12 knots, and the cable's laying out behind it. So they don't see what the cable's laying over. And if you've driven across like the Columbia River basalts, the topography there is pretty interesting. And so imagine doing that in the dark, not knowing what the cable is laying over. And a little tiny nick can let water into those cables. And so if that happens, it's bad news for the cable. So it's a really remarkable engineering feat. So this is one of the these are big beasts. These are primary nodes up to 1,500 meters water depth. They're in a trawl resistant frame. And they provide really the big power and bandwidth to the other parts of the array. We use a lot of the technology comes out of the oil and gas fields. So we use wet mate connectors so that we can keep the instrumentation power, both the sensors as well as the substations down on the seafloor without having to recover them. These are actually hardwired into the backbone cable. So we had to recover one. I'll show you a picture of that. One of them failed. And we had to recover that. And you just really don't want to do that. So there's a few of those on the network. And again, they all have expansion ports. So as technology evolves, if we want to add other areas, there's some interesting opportunities along the coast to do that. And we're working on that. This was competed through NSF. And one of the things I'm most proud of is this applied physics lab just down the road here. We went through a model because we're a university and a teaching institution. The model was for engineering that we would use young engineers and bring them up through, from the start to the finish. And so these were the smaller junction boxes that are put down on the seafloor, the key experimental sites. They also use wet mate connector technology, and each one of these ports is configured for a specific instrument for its bandwidth, communications, as well as power. These also have an expansion port, so we can daisy chain them together. And there's 2 places that are enough instruments that pretty soon I think we'll be in that position to do so. APL is great because they test everything like crazy. And one of the lessons learned, I think when we first we have both on the shelf and off shelf instrumentation. And I think 8 out of the first 11 instruments that we all use routinely were sent back because of the testing. And changing from batteries to cabled instrumentation is interesting at that time, but they responded really well. And I think that's a big message for the community is we really got the instrumentation much more robust than it was in many cases. And they were installed in 2014 and all have been operational. We haven't had any trouble. And I think, again, that's a testament to the really amazing testing that APL does. The installation was done by the ROV ROPOS. It was rebuilt specifically for Ocean Networks Canada. Has almost as large as ours array, and they got in early. And so ROPOS, which is a Canadian vehicle, they designed it specifically for observatory work, and it's still the only vehicle that can do extensive cable laying. So it has a through-flow lift capability that can lift 4,000 pounds. Our gear, actually next summer, will probably lift something that's very close to 4,000 pounds. Most of our gear, the maximum weights are about 3,200 pounds. They laid 33,000 meters of extension cables. All of those are still operational. And the other really nice design is that they have this latching mechanism, again, that came out of industry. And so it can latch into platforms, and it's really easy to get them through the air-sea interface. It's super efficient, and you can relocate them within less than a meter from getting them back to the seafloor, back and forth. What else? Yeah, so we used the ROV ROPOS for all of the operations until 2015. That was our first operations and maintenance cruise. And then Jason was redesigned to basically mimic a lot of what the Ropos guys had done. And so now since 2016, we've used Jason, but with the amazing number of awards that have been funded, and there was a backup COVID this summer, we used Ropos again. So again, they have elevators that take a lot of equipment down to the sea floor for efficiency. We use a variety, both Jason and Ropos have operations center on the ship. And talking about telepresence, so we've streamed live since 2005. I think 2005 we had 1 million people look at our live stream. But during all cruises now, we stream live 24/7, both on the deck and when the vehicle's in the water. And this is particularly important because we have a lot of outside funding from researchers through NSF and other awards. And so with limitations on the ship, we stream data, video to them. They can communicate back through the cable to us when we put instruments back on, and through VoIP phones. And Ken Feldman has been working with Scripps, has been really instrumental in providing that. So it's a great opportunity. So just to dive in a little bit, I won't go through these again, but I wanted to show you, I'm not going to talk about the coastal array much except to show you this. So this is from 80 meters water depth down to 2,900 meters, which is the basis subduction zone. And we partner with OSU, who they have a surface expression of moorings that go through iridium phones to satellite. But there's no place in the world that has this kind of technology offshore. And, particularly since ocean acidification is exemplified here, the signal to noise ratio is higher than other places. There's big storms, all the things that are driving our ocean and climate change right now are here. And so having this technology in place with all the data open to anybody in the world really brings new eyes, and it's a great opportunity for people that can't go to sea. I tell my undergrads that no matter what data set they look at, they're going to make discoveries because the instruments are all streaming full out. They don't have to worry about batteries or communication issues. So this is I'll just show you this one example. We actually have one of these at the base of axial seamount. So again, the system was designed for operational considerations. This is a 12-foot across two-legged platform. About 7,000 pounds. And one of the great technology things that APL developed, there's nothing like this in the world, is a winch profiler. And it's been it has the platform itself. So we can go in, what Jason or Ropos latch into this. We can, they decouple the cables. We bring them up. There's two different platforms, one stationary, one that goes up and down through the water column 9 times a day. And we can turn this instrumentation in less than a day. So it's a very efficient operation. And it's been a total workhorse, even though they're new, and underwater winches are kind of an interesting thing, but we've done over 40,000 profiles in the oceans, and it's a great opportunity for AI development. And this is just one example. So when you think about ocean acidification and CO2, it's in the news a lot lately. If you're lucky, you get to go out and make a few profiles with a CTD and get samples. But what we're showing here is thousands every single day. We're getting 9 profiles a day. And so this is really unprecedented data at high resolution. And if you just were looking at this for like one day in the summer, you'd miss a lot of the signal. So this is an amazing data set that I think will be coming out soon. So, and this just shows you the data rates are so high. We have 18 instruments co-located. So there's a great opportunity again for AI. And I think we're going to be driven to AI because there's so much data coming in. We actually have to do QA/QC on the cloud now because there's so much data, we can't do it on a computer. So just a couple slides on our cruise. So we go out every summer, 35, 45 days, thanks to UNOLS. This summer was crazy. We had 5 legs. I do a lot of the pre-cruise planning, so there are 154 berths to manage. We had 25 48-foot trucks taking gear back and forth from APL down to Newport. And we had, our operations are very different than science dives. So it's more like industry where we get the vehicle down to the bottom and back up as fast as possible. And typically that might be 1 to 3 hours turnaround. And so we did a lot of dives. And the same with Ropos and Jason, we've done a lot. So a lot of transits back and forth. I won't go through all this, but the students, when they're on the cruise, think it's kind of chaotic. It's not chaotic. It's just flexible, I guess, to respond to different events. So over 200 instruments were deployed, returned. We actually turned one of those big moorings, it took 2 different legs because there's so much gear on the board. And then this time we had to recover and redeploy a big primary node. And so we had to lay some extra cable to do that. And I'll show you what that looks like. So just to give you a sense of scale of what these big primary nodes look like, this is, we had to use a cable ship called Intrepid, and they just put this little video together. So this is, it's sitting on the fantail. So this ship can lay cable. They have a big ROV on board because up to 1,500 meters water depth, we have to trench in the cable because of fishing. And so they were able to go down. What they do is they take a grappling hook. Still amazing they do this. They grapple up one end of the cable. They grapple up the end of the cable. They bring the primary node on deck, and then they join it back together again. And this is magic to me. I have no idea how you join fiber optic cables back together, but they do it on the ship, and it's working fine. So it was down for about almost 2 years, and it provided communications to Southern Hydrate Ridge, and so we were able to reconnect it this summer. But these are big beasts, and we were very glad. I also should say that the technology for that, there's not a lot of people around, so APL had to take this primary node apart and put it back together. One of the things I'm most proud of is since growing up with John, he started taking teachers to sea and now undergrads. And so in the last, we've taken almost 180 students, I think now. We've had 20 of them, 20 undergrads from a variety of different disciplines. And 3 of them from last year were repeat students, so they serve as ambassadors. And one of the things that I also am really proud of is we had 2 students that sailed with us in 2014 and 2018, and now they're hired as engineers at APL. So back to what the fun stuff, no, not fun stuff. The things that I'm most knowledgeable about is underwater volcanoes that I started working on in about 1980. This is just satellite data showing, there's thousands and thousands of underwater volcanoes, particularly in the Pacific, and there's only a handful that we've ever been to. They're probably erupting, many of them all the time, especially on the mid-ocean ridges. But again, we're not in the right place in the right time to witness that. So a bunch of scientists got together and picked Axial Seamount, which is the largest volcano off our coast, underwater volcano that's active. It's kind of a catch-22 if you want to look at underwater eruptions, then you need to instrument a volcano that's going to erupt. It erupted in 1998, 2011. We had cabled it in 2014, and in 2015 it erupted again, and it's poising to erupt again. So one of the reasons that we drive this is that we're studying this is it really drives the face of our planet. Over 70% of volcanism on Earth occurs along mid-ocean ridges again, but we're not there at the right time very often. So and huge amounts of heat, CO2, chemicals, and biological material issue from the seafloor in these systems, and I'll show you some examples of that.
Visualize the most extreme environment you can imagine. What do you see? Mountains, deserts, glaciers? Maybe places like these come to mind. Places with harsh climates, scarce food, and no water.
Yeah, it's all the way up.
But what about a place like this?
It's not going to let me do that. Technology trouble. That's weird. Well, I don't want to, I'm just not going to do it because it's probably easiest to just, it played earlier, but that's okay. Such is life. Anyway.
It played earlier.
Yeah. Best. Yeah.
Visualize the most extreme environment you can imagine. What do you see? Mountains, deserts, glaciers? Maybe places like these come to mind. Places with harsh climates, scarce food, and no water.
We'll deal
but
with
what
it.
about
Anyway,
a place like this? Located 300 miles off the coast of Oregon, an active underwater volcano called Axial Seamount protrudes from the seafloor, looming thousands of feet above the barren seascape. This dark setting has never seen the light of day, as sunshine barely penetrates 600 feet into the ocean.
And then,
at these depths, there are conditions rarely observed on planet Earth. The pressure due to the overlying ocean is 150 times what humans experience on land. That much force is equivalent to having a Boeing 747 jet on your chest.
And so this
temperatures here are cold and constant. Throughout the year, day or night, the water lies just above freezing at 34 degrees Fahrenheit.
So this just talks about,
suddenly, sharply jutting up from the seafloor are columns of rock towering over 5 stories high. These pillars can be enclosed in so much bizarre life that the rock itself isn't even visible. And the strangest part about this ecosystem? Fluids reaching temperatures of 660.
So why do we study that? Why do we want to go there in real time and have a presence there 24/7? Well, there's these things called megaplumes. They're kind of like an ash cloud, but not quite. When there's an eruption, they've seen them. We've gone out to see them after the fact using CTDs and AUVs, but we've never been there right when they form. They're probably supercritical, and so the idea is the ocean crust is water saturated. When you inject 2,000°F melt into that water saturated crust, it vaporizes the entrapped fluids, and it rises in a plume be 20 to 70 meters across and up to 1,000 meters or more below the seafloor, above the seafloor, and it carries with it a lot of chemicals and heat, but it also carries microbes that thrive in the oceanic crust. So it provides this window of the microbes, the biosphere in the ocean crust. It's very difficult to sample. And so that's one of the reasons that we picked axial seamount, and that shallow profile mooring at the base. We hope we'll catch that event at some point, and I'll talk about it in just a sec. So one of the coolest things I've ever seen was in 2011, we were doing surveys of the volcano to figure out where to lay the cables, and it had erupted 3 months earlier. This is a trace of the lava flow. It's quite a large lava flow for scale. It's about 3 kilometers across. And we came upon these collapsed basins where there used to be lava lakes. These are all that brown stuff is microbial mat. And then this white material is also microbes, and they're streaming from the seafloor. High temperature organisms that live at 90 degrees C. They use a lot of CO2, which is why they form. The volcano puts out a ton of CO2 when it's erupting. So they take the CO2 and the warm circulating fluids and basically go through a bloom in the subsurface. And I'll show you that video. In 2011, so this was, we thought it was old ocean crust, but it was just microbes covering it. These are called snowblowers. They've only been imaged like 3 times, and this was the first time we were streaming it live. But you can see all this particulate, it's both microbes as well as they produce kind of a snotty enzyme material. So that's what some of this white is. I think they're really beautiful. This one's called Scotty. We actually did a test of we're streaming this live, and so we had, this is like 3 in the morning, people from Europe writing in and suggesting names for this, but they're nascent, so they don't last very long, maybe a year or so, and then they disappear. But you can see the microbial mats get quite thick. And they've only been sampled a few times. So again, when you're thinking about microbes as well as viruses, this is a great place to look at making new discoveries. So why do we care about these guys? Well, you know, the volcanoes are erupting all the time. They eject masses. Probably we don't, since we've only been to a few volcanoes when they've been erupting, probably a lot of them put out these microbial material, but we're not there again. They have novel organisms. So the highest temperature organism on the planet, we recovered in 1999 from Endeavor segment. And then it was, that was 121 degrees C. And then a year later, they found one that was 122. They can use toxic metals. They can process uranium, for example, dissolved uranium and put out a particulate. So there's interest in bioremediation. And it's hard to access the subsea floor, but potentially there's a very large biomass that might rival that on the continents. And more people are looking at them also from pharmaceutical from the sea. So some of these microbes, if you bring them up and stress them out, they produce different kind of antibodies. They also use them for industry because they have enzymes that can tolerate higher temperature. And so you can process things more efficiently at higher temperature. So a lot of interesting opportunities here. So this is kind of an eye chart, but so this is the summit of the volcano. This is the primary node shown here. These are extension cables, and all the white instruments are core instruments, meaning that NSF funds us to keep those going. And again, all data public. A couple ones to highlight. The ones in yellow are, I'll talk about this a little bit more, are in 2016, NSF opened the door for outside funding. So we have funding from a lot of different industry as well as different communities, and I'll show you that. So all these in yellow are PI-driven instruments. We have some interesting ones. So there's a fluid instrument that takes fluid samples. It can be operated manually or by a computer program automatically in a mission setting. And it takes fluid samples, but it also filters for DNA out of a vent. So the idea is to look at, this is one of the only places in the world where we can look at the evolution of microbes over time with respect to before, during, after a volcano. And a ex-student from here was funded. She's now at Carleton University at an early career award from NSF to look at the viruses and microbes in 2 of the vent fields. And she was out, her team was out there this summer on the Thompson to do that. So I will just show you a couple examples. So we stream live. We focus on a hydrothermal event called Mushroom. So again, this is 1,500 meters down, 300 miles offshore. It can come into your classroom, your living room, streams 3 times a day for about 14 minutes. And I'd never seen this before on an active smoker. So this is about over 200-degree fluid that's issuing from this vent. And these are all animals that they're porous. So there's warm water leaking out, sometimes very hot water mixing with seawater. But I think this octopus must have been in a sauna or something, but I'm surprised it didn't burn its little feet off. So every twice a month, we stream it for 24 hours. And then once a month, we stream it for 3 days to look at the impact of light on animals as well as other things. We're fortunate to have incredibly high resolution bathymetry maps. So MBARI has been very generous. They go out there almost every year now with their AUV to re-image at centimeter resolution, the caldera, so they can look at uplift and deformation, and they provide us our maps. So this is the infrastructure in this small hydrothermal field called Ashes, and you can actually, it's good enough to pick up one of the junction boxes, even the HD camera shown here, and then we photo mosaic the chimneys to look at how they evolve over time. And this is a great student project that's going on now. So they're using these data. They also photo mosaicked it, so we draped out over the bathymetry, and so they're making a geology, biology map of the hydrothermal field for one of their projects. I won't do much of this, but these are spectacular. You've probably all seen these black smoker chimneys. There's a lot of, because we don't have a detailed time series of the biological communities in very many places. This is a great place where these are the earliest colonizers of the highest temperature worms. These things are very dynamic, so the chimneys fall over, regrow. And so again, this is another area where the students are really picking up and looking at all the imagery that we have and mapping out the changes in the macrofaunal communities over time. So one of the drivers for this, there's a very intense, very strong geophysical community looking at the volcano because of its deformation and seismicity. So we have a lot of, not enough, but we have a great subset of seismometers and hydrophones out there. And those yellow dots show that. Again, all this is streaming in live. Navy has considerations. So we actually have a special called the Antelope system in our shore station. And the tier 1 sensitive acoustic data go to the Navy, and then they sometimes take part of that, and sometimes, but mostly they give it all back to us. And so on April 24th, William Wilcock here at the UW, who's a geophysicist, was looking at the seismic activity and emailed us and said, you might want to look and see if your array is still functional. So we had seismicity, the scale, you can't hardly see it, but over 24 hours, there were over 8,000 earthquakes. These are small earthquakes, which is why we don't often know the volcanoes are erupting. You'd never feel them from shore. So they were on top of each other. So thousands and thousands of earthquakes over a 24-hour period. And then so that was going on. And then there was a seismic crisis. And so we knew there was eruption. And then on top of that, this is a different kind of, these are waterborne signals or acoustic signals from the hydrophones. And the geophysicists got together. So this was April. We went out in August that summer, July, August. And what these are underwater explosions. And we were able to go out 3 months later with the work they had done and dive on this eruption here. And I'll show you that. It was quite a large eruption. So the spreading center runs right through the volcano here. And there's a northern fissure, which is where the volcanic eruption occurred. There's some really cool phenomena, which you may not expect. So the moon actually impacts both the seismic activity as well as the venting. So before the eruption occurred, the seismic activity was very well correlated with lunar signals. So at low pressure, it's easier for the cracks to form and expand. And so the tides really drive seismic activity. After that, it gets kind of overcome. A lot of the stress is relieved, and so you don't see that relationship after that. But you also see this in temperature in the hydrothermal vents, and this pumping probably in the hydrothermal vents, it pumps in oxygenated seawater. Hydrothermal vents don't have any oxygen or sulfate, so it's a great energy exchange in the walls of the chimneys that probably drive some of the hydrothermal communities there. Unfortunately, this is horrible because maybe I can get it to play later. But if you could hear this, these would be underwater explosions. And it turns out that all those red dots were underwater explosions. And you can hear it? That's so weird. well, I'll play it for just a second, I guess. So these are really loud. And what's interesting, so there was over 30,000 of these explosions occurring. They weren't quite sure what they were at the time, but it's also in the range that whales can listen to. So there might be some interesting relationships that people haven't thought of there. So it's really, I can listen to it for a long time. So I had a student on ship. I had a student on the ship that went out with us, and he mapped the whole lava flow out. And just to give you a sense of scale, so we dove on, not being my friend today. We dove on it 3 months later with Ropos. And to give you a sense of scale, if you're wandering around Seattle, you know, if you're standing up here, look up at the Space Needle, and that was the thickness of the lava flow. So over 400 feet thick. We drove up because of the great locations of the both using the EM system on the Thompson, and also because of the geophysical work that had predated that, we dove within 10 feet of this eruption and went up. It was quite a steep, almost angular repose eruption. And the whole summit was covered with these microbes again. So they do seem to be 3 months later. We went back the next year and they weren't there. So this is the old lava flow. And all that yellow material is old microbial stuff, well, 3 months old. This is what one of those explosions look like. So every time a pillow basalt cracks open, the toe of it cracks open, it emits gases and it causes an explosion. So, and then this is what the summit of it. There were acres and acres of these microbial mats and really small, in this case, really small snowblowers. So. One of the things that surprised me from this, Jackie at Western Washington, she had done a lot of work on Loihi, looking at hydrophone data, and was for seismic activity and eruption behavior. And she looked at the hydrophone data and showed this, instead of punctuated explosions, it was this diffusive signal that lasted quite a long time. And from thinking back to what she'd seen in Loihi, what it looks like is these were fissure eruptions. This is you know, not underwater, but this is what it looks like. The seafloor, a fissure opens up, usually like 3 meters across, something like that. And there was enough hydraulic pressure from the magma coming out, or lava coming out, that it actually caused fountaining at a mile deep underwater, which is always surprising to me. And some of the documentation for that as we went, this is one of the bottom pressure tilt measurements, which I'll show you data from in just a minute. This is actually ash. So there was ash forming during this eruption. This is probably the only place that we know about where we might be able to predict the next eruption. This is work from Bill Chadwick at OSU and NOAA and Scott Nooner. So they had uncabled bottom pressure tilt instruments. These are very sensitive. They measure when melt is being put into the seafloor, the whole summit of the volcano rises and tilts upward. And then when there's an eruption, the lava drains out and the seafloor collapses. So they had battery-driven instruments out there that they would go out every summer and recover. So this was the 1998 eruption. So the seafloor rose about not quite 3.5 meters. And then the eruption occurred, it dropped down. And then slowly, this is melt being injected in the subsurface. And then 2011, that was the eruption. And then 2014 is when we started getting data. And so this was the 2015 eruption. And so Bill's developed these really nice models about that you can go online and look at. And you can, this is the trajectory of the response of that melt being ejected in the subsurface. So a lot of that chatter is sometimes it kind of decreases in the cycle of the melt and how it impacts the volcano. And when it was like this, we're thinking if you project that line, we're like, oh man, it looks like 2022. And it makes me nervous because we escaped one eruption that was close to our array. But it's slowed down now in the earthquake activity. This is all tightly coupled to earthquake activity. So it may pick up again, but we can look at this, we can look at it every single day. And so now we're pushing it. He's pushed it out to 2025, 2030, something like that. I'm almost done here. So I did mention that, again, this is, I think, a testament to our and NSS vision in 2016. No, 2006, Margaret Leinen on a big community, there was like 300 people workshop for all of OOI that we're a subset of, and said, if you build it, they will come. And in 2016, when NSF opened the door, you really do see this. So we have there's been over 75 awards total for PIs and co-PIs. There's 35 institutions. And then I think it's really nice. We have a diverse funding portfolio, which is what we were hoping. So NSF, ONR, NASA, BOEM, and we have a big long-term project looking at hydrates in the crust at on the margin from Merum, Germany. So each year we've been lucky in getting a few more programs funded. I'll just highlight about a couple of those and then I'm out of here. So this is just one of them. This was just funded, so it doesn't have an NSF award. But the hope is that, so this is to put some more benchmarks out there to keep CTDs out there from Bill Chadwick. It shows RRA as well as a benchmark. So he also goes out there with the vehicle every year and sits on these sites for measuring pressure, high resolution. And this extends the duration of that project. There's also, he's put in CTDs that are cabled because one of the remarkable things, we think it's a hypothesis now, is during the 2015, as I mentioned, the hydrothermal vents are boiling. And so that creates fresh water and the salts stay in the subsurface. And it looks like there was this cloud of briny fluids that came out after the eruption in 2015. And it turns out there's organisms called halophiles that require up to 28% sodium chloride. So there's a lot of interesting connections that people hadn't anticipated necessarily between eruptions and the organisms that live in the subsurface. And then they also will go out there with MBARI again and do repeat high resolution surveys to look at the deformation over time. This was a really nice experiment that got funded. Dana Manolang's an engineer at APL, and I don't know of any other long-term acoustics nets, but this summer we installed these Fetch Sonodyne instruments that have the transponders, but they also measure pressure and temperature. And there's one cabled here, and then there's one up on the western wall, one on the eastern wall, and one near central caldera. And the idea is that they'll range back and forth on each other. And with that, if you know the sound velocity profile well enough, you can look at the deformation in very, very high resolution. And part of the driver is that you may not realize this, but that ring, this is a big collapsed area, and these are about 100-meter tall walls. And this is we call it a ring fault. So there's a lot of faulting activity, and that faulting also, we see it when there's an eruption going on. And then William Wilcock and Maya Tolstoy got funded to put out, this was delayed for a few years, a much larger seismic array. These are battery operated, so they'll be recovered from the seafloor again to look at more detailed in terms of how melt is migrating in the crust. I'm almost done here. So one of the things that acoustic net was installed, one of the reasons we'd like to do that is the dream, and this is John Delaney's and one of Dana's dreams, vision is that eventually we can have autonomous underwater vehicles. Technology in the oil and gas field and offshore energy environment has developed really nice AUVs with different kinds of sensor packages on them. They go into a garage, power up their batteries, download data, and go out and do their missions. And so this could provide the first opportunity, which I would hopefully I'll be alive to see, is to look at an eruption as it's happening. You could see video right when the eruption's on the seafloor, which I think would probably pay for the vehicle. If you can hear this, these are wonderful mammal calls. So we have broadband data streaming. It'll be up over 240 hertz eventually. But one of the cool things that a discovery that has been made looking at 10 years of data at axial seamount is the vocalizations of fin whales have changed over time. Their calls have actually gotten quieter. And one of the hypotheses is that with the moratorium on whaling, that the whales don't have to sing as loud to be heard from each other, that's my favorite hypothesis. And then I wanted to mention this because to me, it's one of the most exciting things I've heard about in decades. To me, it's like putting the first telescope, building the first telescope, but this is underwater. And so there's a new system, well, relatively new now, called DAS, distributed acoustic sensing. And basically it turns, depending on, right now you have to have the cable powered off, and we had it cable powered off to work on the shore station for 4 or 5 days in November last year. And William led this, but it was the first community experiment to do this ever. And so basically you hook up your own DAS system and it interrogates the cable, and it reaches, depending on the ping rate, you can reach up to 100 meters offshore, and it turns, again, depending on that, every couple of meters of the cable into a sensing device, so a seismometer, for example. So there's a ton of interest right now. It's exploding around the world for looking at, they have in California to look at earthquake events. They have them to look at glaciers. So there was an experiment in Antarctica, and NSF funded the first experiment of its kind. And this just shows you, these were screenshots. And I should say, it was a requirement to pass it. The Navy was very interested initially. They passed through a very specific chain of command, all the data, and they gave all of it back to us. And this is just screenshots during the experiment. But William Wilcock gave a talk, and there's a paper coming out. But I think one of the unprecedented opportunities is in that 4 or 5 days, there was tens of thousands of fin whale calls. And so again, a great opportunity for, you're going to need AI and something like that. It's also super high data rate. So in 4 days, you can collect 26 terabytes of data. So how you deal with that. And yeah. And finally, just 2 more slides on looking at, I know I'm probably going over, but we can pick up tsunamis. And that's really important. If you watch the Tohoku learning lessons after that, it's really important to have tsunami warning systems near shore, which we can do with the cabled array. And then we also have a live seismic stream. And so there's interest in getting our data into shake alert for terrestrial systems. And looking forward, you know, Japan put in probably $1 billion for DONET, which is an underwater cabled system for operational considerations. That they get great science out of it, but most of the instrumentation is actually built into the cable. And so, you know, the magnitude 9 is coming. We don't know when, but it is going to come. And so there was an opportunity of funding from the Moore Foundation. And there was a big workshop here to look at what an offshore system might be, because depending on where the earthquakes, if they're down on the Mendocino and start migrating northward, that whole, historically, this whole Cascadia system has basically unzipped. And depending on where you have where it initiates, you might get up to 3 or 4 minutes warning of that event coming. So you can imagine if you're in Seattle, you could turn off power and gas, things like that. And this is the way of the world, right? These are all small, most of these, well, these are telecommunication cables, but then there's a lot of small observatories, a lot of them for warning systems that are being installed. And China's installing, I don't know if they finished it, 200-300 kilometer ones for science, but I'm not sure that will stay just for science. I don't know if we'll see those data or not. If you want, so we have a nice website. We have thousands of images that are open to anybody, a lot of video, best hits the students have made. So those are, and then we also have now 600 data streams coming in live every day. With a nice, it's hosted on the cloud, so it's much faster to look at the data. And I think that's it. So thank you so much.
Wow, that was really fast. So nice to know what the ships are doing when they're out there.
Yeah.
So we'll take questions from the audience and also look on. That was a fabulous presentation. Thank you so much.
Thank you.
Pablo.
As a software guy, I have a really naive hardware question. You talked briefly just about power cable. How much power do you need to drive out there to run all of this stuff? And is it just basically high voltage AC?
So we have, the question is, how much power do you need to drive all this stuff? So within the fiber optic cable, there's depending on how much power you want from shore, there's copper in there. And so we take the copper. So right now we have, it's maxed out at 10,000 volts, but and that gets downgraded to 375 so that we can get the instruments, but we can upgrade that over time too. So, and then we have 10,000 gallon generators. So if the power goes out, they kick right in and keep it going. So we don't use anywhere near the power right now, except the biggest power hog right now is the shallow profiler moorings. Yeah, going up and down. So.
How many instruments do you have in harm's way?
How many? The question is, how many instruments do we have in harm's way? Depending on the harm that you want to think about. 2 examples. One is axial seamount. There's about 22 cabled instruments. We've made a specific plan to put. We know where the more recent eruptions have been, and so the big substations, the primary nodes, which are expensive, we put away from where there's been historical eruptions. The other ones, you know, it's not cheap, but it's not anything compared to one of the primary nodes. And then the other point is, you know, when a magnitude 9 occurs, we probably have, I don't know, 80 instruments or something along the margin, something like that. But we got, one of the things that John did and Delaney initially did was he hired people from the telecommunication cables. And one of the lessons you saw in Taiwan when there was a big eruption and a big earthquake, and a lot of there were like 7 fiber optic cables that snapped. They would actually lay them parallel to the slope, and so one of the lessons is to learn it perpendicular. So maybe we'll be lucky and keep them going. But there was one of the ways. If you saw, there's the hope is for early warning system that we would have redundant shore stations so that you wouldn't lose the whole network. Good question.
Alice, you go.
Alice? Hey,
I'm
Alice.
just gonna ask about your vision program, that participating in the vision program.
Nope, not at all. No. Also, the question for the Visions program, are they all UW? And the answer is no. So because we get state funding for education for the Thompson, they donate some ship time to us every year. Hopefully that will happen with the next charter. But so a lot of them are funded, there's no cost to the students, everything's covered. So, but a lot of them are from the UW. But we also have a longer term relationship with Queens College. We've gone to Western, OSU, so there is some diversity. We also have artists, I haven't talked about that, but artists and filmmakers, and there's no requirements to go to sea. I think it's really important to get new eyes out there. And so now an ex-Vision student is now in the White House, working on environmental policy things. So you never know what's going to happen. So, and there's actually one in this room.
Sarah, is that you back there?
Yeah, certainly there's some nice data proposals that have been funded. There's a lot of interest in AI, so they're definitely going that direction. In terms of technology, because we live on the Cascadia subduction zone, some of the instruments, there's one site on Axial that's been a really great collaboration among different PIs that have been funded to develop new geodetic instruments because it's a higher signal to noise ratio there. But what they're finding is it's high enough, the resolution is high enough that the hope is they were developed and funded by NDSF as part of that to say, okay, if they work here, we're going to try and move them to the subduction zone. It just so most of the Cascadia subduction zone is locked, but it looks like right where we laid the cable, there's a big seamount that was brought under the crust, under the sediments there. And it looks like it's the only place along the Cascadia subduction zone that's unlocked. And so the hope is to develop new like GPS systems out there. Right? Canon has some nice GPS where they have GPS stations talk to a sea, what do they call it? Sea drifter that they can hover and talk to that and then get the data to shore that way. So I think that's one of the great things about these systems is the new technology and new. We've been in communication with Microsoft, and one of the leads in eScience here is from my ex-Microsoft. So there will be those connections. Yeah, we have to have more AI. There's no way that we can deal with the data.
We have a couple of questions.
Max Kramer from University of Hawaii asked, can a volcanic megaplume be compared to a sediment plume expected from abyssal mining?
Ooh. I was just going to see if I could get the over my laptop, so I can't do it. Yeah. So there was one of the, I guess, most advanced, longest term looks for undersea mining was in Papua New Guinea. The question is whether the plume from deep sea mining, what it's going to do. I don't think so because there's not as much energy and the plume is probably going to be a lot denser. And so it probably won't reach as high up into the water column. That's my interpretation.
What's the typical volume of data you get from the array?
What's the volume? So we have a HD camera. So that's and it's unresolute and it's not compressed at all. So that's the highest. That's on its only 10 gig line, and we want to go to 4K. The DAS system definitely, you know, terabytes a day, definitely will push it. And there's opportunities, maybe we won't need the power for the cable shutdown. So I think DAS will drive new ways of how we store data, like where do you put it, right? How do you get, so right now for that data set, we store it here at the UW. And then people have to provide their own hard drives because there's really the cloud is not optimal for big data sets. So, yeah.
Lance.
I'm curious, where do you see teleoperation, telepresence for the future? I mean, do the scientists and PIs really need to be on the scene anymore?
Yeah, so the question is, in terms of telepresence as a scientist, where do I see it going? So I've done telepresence with Ballard out at Lost City. For family reasons, I've had to stay on shore for 2 years and basically help run the cruise from shore. My personal perspective is there's nothing like, I think there are reasons to do it, but that personal communication and seeing somebody face when you're on the ship and interacting and knowing that they're exhausted or not, I don't think you can ever get rid of that. I think it's just critical. It's absolutely critical to run an operation. You know, ROVs, I think there are some components you can do that, but when things break, you know, you have to respond really fast. I think that'll grow. But there's a lot of people things that happen on a ship that I think you just really have to be in the room for. Yeah. Certainly I think the AUV world is going to move that way. They're developing for offshore energy. So, and for oil and gas fields to move everything underwater, right? And do the operations using AUVs and ROVs. And so those will be, you know, there won't be people involved directly in that. They're running them from shore. So I think it'll move that way, but I still think for really tough decisions, I don't want to be on shore and make those tough decisions. There's just too much interaction that goes on. Plus I love it. So I would hate to, I just hate it. It's sort of like using an ROV versus diving in Alvin, right? There's something that happens in your brain that's different than, maybe it won't always be that way, but that's, for me anyway, that's true. Thank you.
All right. So I think Brandy's probably going to say something.
Yep, yeah, yeah. And if anybody wants any of these, we're delighted to give anything that's helpful.
What does somebody Google to go find this online?
Well, Interactive Oceans, but you can also just write me.
Okay.
Just write me directly and
Right, directly or Interactive Oceans.
thank you guys.
Go to your lunch.
Thank you for everything you do.
Back here at 1.
For those of you online, sorry, the audio stopped when we quit sharing the screen. But 1 o'clock, we'll have another round of plenaries. And then at 2 o'clock, the managers meeting. If you're a manager, you can attend remotely. And other than that, we'll be doing tours. So you'll have a light afternoon. Thank you.
That was so great.